Hello and welcome back to another lecture for your Earth Science course. This one is looking at beyond our solar system. So in this presentation we'll discuss briefly just really the development of stars themselves, the story, the linear story in which they go through, and just kind of throw out a couple key terms. It's a very light, quick presentation, but I wanted to make sure that we kind of broke this up into three smaller presentations to make it a little more palatable. So let's begin. So the first thing is the characteristics of a star. So obviously stars are the first thing that people began observing. There's lots of very, very interesting and fascinating cultural interpretations and observations of the then moving from stars but connecting the dots, looking then at the constellations themselves. So what is a star? Well, a star is a massive ball of plasma that's emitting light throughout the universe. While we only have just one star in our universe, which is the sun, there are billions upon billions of them throughout our galaxy and then beyond. Now, a constellation is a grouping of those stars, and they're named after mythical characters. We actually have 88 of them total. Now, that not all 88 are observed on any particular night at a particular latitude. That's because the stars are and from our viewpoint all around the planet itself and to beyond. So we actually get to see them seasonal. We get to see through seasonal changes and latitude changes. We can observe all the constellations. Now, what's interesting about stars, or these suns in particular, is that the color is a clue to its actual temperature. So the hotter it is, the more blue it appears. So that being said, if you've ever seen anyone welding or you've seen anyone use like a blowtorch, when it's really, really hot, you can see that the flame goes from red to blue. When you transition from that red to blue, the blue means it's even hotter than you anticipate. It's hotter than the red, right? So a couple different pieces. So I labeled a slide, infinity and beyond. So we live on a planet. Earth, right? And our planet is part of a solar system, and then our solar system is part of a galaxy. So I guess kind of wanted to make sure people understood those differences. So we are a planet, we're part of a solar system, our solar system is part of a galaxy. Because some people often ask, well, how come we can view our galaxy? Why can we view the Milky Way? And it's because where we're positioned, we're able to see the greater part of it. We see, just a piece of the pie, right? We're part of it. So again, this is a little diagram that shows planet, solar system, galaxy. And for our purposes, we're looking at just these three different types of galaxies. There's a spiral, elliptical, and then the irregular galaxy. And these are the three galaxies that have been observed. There's actually a fourth one, but it's a mixture of two. But these are the three that we're looking at. And again, if this interests you, we have full classes that spend 16 weeks on this. We're spending this a very short amount of time. So I'm only asking you to understand the fundamental of the names, and that these are observed differences. We can observe the spiral galaxy. We can observe that's an elliptical galaxy. We can observe that is irregular. So that's all I'm asking you to do. Well, speaking of infinity and beyond, how do we observe differences in sizes? Well, we can use binary stars and stellar masses to actually understand the general mass between two different objects. So a binary star is one of the two stars revolving around a common central mass under their mutual gravitational attraction. So in this case here we can see that here's the central mass, it's being leveled, and here are two, in this case, stars. They are orbiting, they're rotating around this central piece, but they are of equal mass. What's interesting about that is that it is obviously in this diagram, because it's not a real picture, it's a cartoon. They look of the same size, but we also find that in some cases things can change their size based on our observation. That just deals with angles and then their distance. Then looking down here, one star is twice as massive as its comparison. So we're able to then compare the central mass, compared it on this piece, and then we have 2 units of these reds that would fit within there. So anyway, the main thing is that what is a binary star? The binary star is one of two stars that's revolving around a point that we know its absolute size. So then based on that, we're able to then create relative understandings of the sizes of other stars that are within its plane. Then moving binary stars are used to determine star properties, and usually most difficult to calculate the mass of other objects. So when we're looking at two objects, from our perspective, they look like they're right next to each other, but one looks bigger, one looks smaller, right? But the reality is they're both of the same size. So if we're able to use a particular mass to measure and go, oh, wait a minute, they are of the same size, just when they're closer it looks bigger, and when farther away it looks smaller, we're able to understand that. So moving on to the next slide, it says measuring the distance to stars. So there's this thing called the parallax. The parallax is the shifting of the apparent position of a star due to its orbital motion to the Earth. So looking at this diagram, here's the sun, there's the Earth throughout its cycle. So it's taking photos perhaps during this time of year and that time of year, which in these both cases happen to be uh, in this observation, I would assume they're probably equinoxes, but nonetheless, looking here, we can see that at this location, that star is that star right there. But the exact same place, just 6 months apart, now it appears that the star has been moved to the right. So what we have is this, first you're looking at the line of sight, and these are the parallax angles that we're talking about, and how this shift, the background, shifts the observation of where the star is. This star, it has not moved. These have not moved. It's just based on your perception of seeing one looking like this and one looking like this. It's the exact same thing. You're just shifting the angle in which you are observing it. So it says here, again, the parallax is the shifting of the apparent position of a star due to the orbital motion of the Earth. The nearest stars have the largest parallax angles, while those that are farther away are almost too small to measure. So a light year, again, is the distance that light travels within a year. It's about 150 million kilometers or 93 million miles. So these are very large distances that we're discussing when we start looking at the distance of some of these stars. So anyway, the idea is that if my hand here, this is the apparent shift versus that star. So if it's very close to me, if I'm just changing my perception, it seems a lot greater than if it's next to each other. So that's the idea there. So how do we measure the distances to stars? Well, it becomes complicated in that sense, because we're trying to, if you're observing one night and then you go back to redo your research and you're observing it 6 months later, you're getting a whole different perspective. That's why it's important for us to understand these stationary locations, these binary stars that we're able to then relate everything around it with. All right, so since we've mentioned stars, let's talk about the life cycle of a star. So now this is a Hertzsprung-Russel diagram, and what this diagram is showing is, first, it shows temperature of the stars. So as we've already acknowledged, that the bluer the star, the hotter it will be, and then the redder, it's still hot, but it's a little bit cooler in that sense. So we can see that there's different sequences. You've got the white dwarf sequence, the main sequence, the giants, the supergiants. So this is a diagram showing the relationship between absolute magnitude and temperatures of the stars. Now a main sequence star is a star that falls into the main sequence category diagram. So you're going to be able to follow it throughout its main sequence. So our sun is right here. So our sun at some point will go over here and burn out, and then it will be gone. So we're seeing that there's a sequence in which these stars suns are able to go through. And then we have these others that do not fit that main sequence. They're a little bit different. You've got white dwarfs, giants, and supergiants, all of which of these are covered throughout the text that we're reading through. But I wanted to just put this diagram out there because it does mention it, and we do mention it throughout the modules, that we do have this main sequence of a sun, and we can watch from here all the way to the fact that it finally just ends up burning out. It becomes too cold. So let's talk about each one of these. So a red giant is a large, cool star of very high luminosity. Supergiants are very large and bright red stars. A nova is a star that explosively increases with brightness. So so it's essentially an explosion. And then a nebula is a cloud of gas or dust. So this one here is just showing essentially a nebula formation. So again, you have red giant, supergiant, nova, and nebula. These two here, the giants, are part of this diagram here. But again, we do make reference of what a nova is and a nebula. So let's look at the star birth. So this is the main sequence of a star. So 1 is the main sequence. 90% of its life will remain within that first sequence, which is a few million years. The next stage, the star or sun will be then turned into a red giant. The surface becomes cool and then becomes red. And then the last part is burnout and death. That's the third step. So eventually we'll run out of the fuel and will actually collapse internally due to gravity. Low mass stars would then become white dwarfs, in which they turn into pretty much ice crystals. So this is a little table summary of evolution of stars of different masses. So depending on the origin, the original mass of that star or sun, will also decide what will happen to it. So as we can see here, a sun is equal to 1. So we're looking at if we had a mass that was 20 of our suns, it would turn into a black hole in its final stage. Our sun will turn into a white dwarf. If we had 6 suns that were together in full mass, in main sequence would be white, it would be a giant, it would go to a supernova, and then go to a neutron star. So this little table and diagram is just kind of putting in perspective the story in which our stars will go through the sequence. This is probably a little more easy to get through than looking at something like this. So perhaps maybe it helps you to draw them out. Draw this main sequence piece out and then block it off with this table summary. Maybe that'll help you kind of put it in perspective. But anyway, I think it's kind of interesting because at some point our sun will turn into a white dwarf, and that's obviously very, very far off into our future. That's not something we're quite concerned with, but it's still interesting to study those different things because it's like, well, in order for us to understand how our planet survives, we have to understand the surrounding environment to see where that goes. So then moving here, I know I apologize for the quality. I couldn't find a better one. But this is just showing that sequence. You go from nebula, protostar, main sequence, white dwarf, and then at some point when it completely loses all of its mass, turns into a black dwarf. But white dwarf is where we usually find that it stops when it's just the ice ball in that sense because it collapses due to gravity. Here we have a medium mass, so nebula to red giant, and it goes to white dwarf. And then here's a massive star. It goes from nebula to main sequence, red supergiant, supernova explosion where it finally gives out and can turn into a neutron star or maybe even a black hole. So again, this little diagram pretty much represents the table on the other side, but I just thought this was different in order to observe it in an image and more of a cartoon. So what's the walkaway? Well, the walkaway is that we understand that there's a sequence in which our stars go through. We also now understand clearly that our sun is a star that is within our direct solar system. That being said, we now understand that depending on the mass of that star from its birth of being a nebula, depending on that size of its formation will depict the story, the stage in which that star will go from start until it goes to finish. So what I would be, if I were you, what I would be making sure that I understand is I'd understand that there's a sequence. I understand that there's a name in which we use to understand the sequence. I understand that there are 3 real stories that I can look at, where I go from here to there, here to there, here to there. These would be great short answer discussion pieces to say, well, let's say you're dealing with a very massive nebula star. What do you expect what do you expect to happen? I'm not going to make you sit down and try to calculate how long it's going to be. That's not, for this purpose, this course, we're not looking at that. We're looking more, okay, if we had to look at the sequence, the story, what would I expect? Oh, well, I would expect a massive mass to turn into a black hole. Right? And this is the steps that we would go through to go from here, 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 here. So make it very simple on yourself. Just understand the steps. Make sure you write that out so you got it. Again, short presentation, I know, but this was all one big presentation that I broke up into 3 smaller ones. So, but anyway, I hope you enjoyed. Again, if you need anything, don't forget to reach out. I appreciate your time, and we'll talk soon.